Hello everyone, happy to see you here and welcome back to my channel Higher Mathematics. Today we have a really interesting question, 1 to the x equal to minus 3, and we need to find our x. In previous videos I solved 1 to the x equal to 3. Today we have 1 to the x equal to minus 3, and right now let's try to solve it. First of all, let's imagine that you study at school and you have this challenge, for example, on your exam, yeah? And how will we solve this challenge? First of all, we will apply natural log on both sides. So let's imagine we are studying at school and we're going to solve this question. So first of all, we're going to apply natural log on both sides. So we have right here natural log of 1 to the power x equal to natural log of minus 3. Okay, right now this x will come down right here because this is like the main log property. As a result, what we will have? We will have x times natural log 1 equal to natural log minus 3. Okay, right now this is like a constant. We don't know exactly what it is equal to, but we divide both sides by natural log 1. So right now let's divide both sides by natural log 1, and as a result our x equal to natural log minus 3 all over natural log 1. And you're sitting on your exam and you'll be like, okay, natural log 1 equal to 0. Right now natural log minus 3 does not exist. Okay, so let's write does not exist right here, and you'll be sitting like, okay, I can't solve this challenge. This is absolutely weird question. And if you study at school, this is enough for you because you don't know about complex numbers. So right here you will write that right here we'll have no real roots. Okay, and this is your answer, and this is absolutely correct answer in terms of your school because this is enough for you right now. But in terms of math, we can solve this challenge in terms of complex numbers. Okay, if you don't have like real numbers, we will solve this challenge in terms of complex numbers. And let's do the thing right now. First of all, there are a lot of approaches, but I'm going to show you this one. This approach according to Euler's identity. So let's split this solution. So this is like a real part right here, so we don't have real roots. And right now let's write our Euler's identity. E to the power I times theta equal to cosine theta plus I sine theta. Okay, this identity is really great for us because right here we have a complex unit, and as a result we know that we don't have like real numbers right here, root in real numbers, so we are going to solve the challenge in terms of complex numbers. For those who don't know this, who don't like this identity, I want to prove this real quick. So for example, we're gonna plug in theta equal to 0. For example, if theta equal to 0, as a result, what we will have? We will have e to the power I times 0 equal to cosine 0 plus I times sine 0. Sine 0 equal to 0 and cosine 0 equal to 1. As a result, e to the power 0 equal to 1. So we have 1 equal to 1, which is absolutely correct. So this is a great identity for us. But why I write this identity? Because this is really helpful identity, because we are going to apply a substitution right here. Okay, what substitution? So let's split it. This is our second step to remember about Euler's identity. And we really need this identity right now because we are going to plug in a substitution. So how our substitution looks like? Our substitution, theta equal to 2k pi. And let's plug in right here this theta into this Euler's identity, which is absolutely correct by k, but k right here is integer. Okay, k is integer, and k, for example, 1, 2, 3, and a lot of these values. So let's plug in this theta instead of this into this Euler's identity. So as a result, what do we have right here? E to the power I times 2k pi equal to cosine 2k pi, okay, plus I sine, right here we have 2k pi. Really great. Right now, let's look closely. What do we have right here? We have absolutely correct equation, absolutely correct identity, and right now we're gonna plug in k equal to 1, k equal to 2, and k equal to 3, and we will see what will happen in this question. This is really interesting part right now. So first of all, let's plug in right here k for k, so for k equal to 1. When k equal to 1, what we will have as a result? E to the power, so from here what we will have? E to the power I times 2 pi equal to cosine 2 pi, okay, cosine 2 pi plus I sine 2 pi. Okay, when k equal to 1, we have this identity. And in previous step, we proved that this is a correct identity. So as a result, cosine 2 pi, we know that this is equal to 1, because this is like a period of cosine. So we have 2 pi, this like a period, 1, 2, right here. And right here we have sine 2 pi equal to 0. As a result, 1 plus 0 equal to 1. So this identity, when k equal to 1, this identity equal to 1 on the right side. Really great. Let's check real quick for k equal to 2. Let's do this right now. So when k equal to 2, so for k equal to 2, as a result, what we'll have? E to the power I times 4 pi equal to cosine 4 pi, yeah, plus I sine 4 pi. Okay, when we plug in, instead of k, we're gonna plug in right here too. We have this equation. And right now, let's look closely. Cosine 4 pi, as I told you before, this is like a period. So we have right here 1. And sine 4 pi, this is also like a period. So we have 0. As a result, this equation, this expression on the left side equal to 1 plus 0 equal to 1. Really great. And right now, let's look, for example, once more. For k equal to 3, let's see what will happen when k equal to 3. So for k equal to 3, as a result, what we'll have? E to the power I times 6 pi equal to cosine 6 pi, okay, plus I times sine 6 pi, okay? And right now, cosine 6 pi equal to 1, because this is like a period, and sine 6 pi equal to 0. And right now, 1 plus 0 equal to 1. And this is really interesting moment right now, as you can see. When k is integer, so k 1, 2, and as a result, for example, we can check real quick 4. It changed nothing, but it helped us a lot because, for example, the last one, let's k equal to 4. As a result, what we'll have? E to the power I times 8 pi equal to cosine 8 pi, yeah, plus I times sine 8 pi, okay? Right now, cosine 8 pi, the same 1 right here, and sine 8 pi, the same 0. So as a result, we have the same 1 on the right side. And here is the main thing for me. Take a look closely. When k is integer, 1, 2, 3, 4, and as you can see right here, like k equal to 5, right here 6, 7, and a lot of these k's in terms of integers, yeah? This expression on the left side, this expression, this doesn't matter. Right here we have a period 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. All the time this expression is equal to, 1. And why this is really important for us, because we're gonna write the final equation after these 4 lines. We're gonna write this thing. So the main thing from this explanation, that e to the power I times 2k pi, so this expression on the left side in terms of k, equal to all the time 1, equal to 1, when k, of course, is integer. So in this case, k is integer number, and k is, for example, let's go with 1, 2, 3, and a lot of these values. So this is our expression after explanation, this Euler's identity. So this expression equal to 1. But in the beginning, what we had in the beginning? We had that 1 to the x equal to minus 3. This is our equation that we have in the beginning. And right now, instead of this 1, let's plug in this expression, because we know that this expression equal to 1 when k is 1, 2, 3, so k is integer. So right now, let's gonna plug in this expression instead of this 1 in our equation. So let's do this right now. So what do we have as a result? We will have the next thing. We will have e to the power I times 2k pi to the power x, yeah, to the power x, equal to minus 3, okay, equal to minus 3. Right now, how can we solve this? How can we solve this equation? First of all, let's apply natural log on both sides. As a result, what do we have right here? We will have the next thing. We will have natural log of e to the power I times 2k pi x equal to natural log minus 3. Really great. Right now, this power will come down because this is like the main log property. As a result, what do we have right here? E times 2k pi x times natural log e. Okay, so this power will come down, and we have natural log e equal to natural log minus 3. Okay, really great. Right now, let's divide both sides by e times 2k pi. Okay, as a result, what do we have right here? We're gonna divide this left side, so I times 2k pi x natural log e. We're gonna divide by I times 2k pi, I times 2k pi, and equal to, we have natural logs minus 3 divided by I times 2k pi. And right now we're going to cancel this one, and we're going to cancel this one. This natural log e equal to 1. As a result, we have only our x on the left side. So x equal to natural log minus 3, natural log minus 3, and divide all of the thing by this power, I times 2k pi, I times 2k pi. Right now, we can multiply both sides by, so numerator and denominator by I. Okay, why we multiply it? Because we will like remove this I from our denominator. So right now we're gonna multiply our numerator by I and our denominator by I. In our minds, we know that I square equal to minus 1 in terms of complex number. And we will have this I right here because I gives us I square. So as a result, the general sign will be minus. So we have x equal to minus I times natural log minus 3 and all over 2k pi. All over 2k pi. 2k pi. But we know that k is not equal to 0. Yeah? K is not equal to 0 because we have it in our denominator. K is integer. Okay? And that's it. K is 1, 2, 3, like integers number 2, 3, and a lot of these values. Right now we're going to simplify this expression, this answer, because natural log minus 3, we know that natural log 3, this is absolutely okay expression for us. We know that this is like everything is possible, and natural log 3 takes place in terms of mass. But natural log minus 3, we know that this argument right here every time need to be positive. Right here we have negative, and if we solve this challenge according to a complex numbers, so right now let's simplify this natural log minus 3, and we will plug in this natural log minus 3 when we simplified it. We're gonna plug in this natural log minus 3 into this expression. So let's do this right now. Okay, so here's our answer, x equal to minus I natural log minus 3 all over 2k pi. K is not equal to 0, k is z, 1, 2, 3, and 4, 5, and dot, dot, dot. Right here, natural log minus 3, as I told before, we can leave it like that, but in the same way, we can rewrite it in terms of complex number and in the same of this Euler's identity. So as I told before, natural log minus 3, let's write the thing right here, let's simplify it, and then we're going to plug in this natural log minus 3 into this answer. So we have natural log minus 3, natural log minus 3. In terms of math, we know that this is like not possible. This value need to be positive, and there's no way that this expression will take place in terms of real numbers, but in our case we have negative. So it feels like right here we have complex number. So let's find this, let's rewrite this expression in terms of complex number. First of all, this is equal to natural log, so this minus 3 can be written as minus 1 times 3. Okay, we can write it this challenge like that. Right now we know that natural log doesn't matter. Natural log, when we have natural log of a product of two values, we can also write it as a sum of two logs. In our case, we have a sum of natural log, so we have natural log minus 1, yeah, natural log minus 1 plus natural log 3. Okay, natural log 3 are really great. Right now, natural log minus 1, let's rewrite it a little bit. So in this new line, let's rewrite this minus 1 in terms of Euler's identity. Because of a period, we can rewrite these expressions of natural log minus 1 as natural log of e to the power I times, right here we have a period, so pi plus 2 pi, and let's go, we can solve this challenge with k because we had k right here. Let's go, for example, with m. Let's write here our m, and of course plus natural log 3. So we have right here plus natural log 3. So instead of Euler's identity, we can rewrite this expression like that. Right now, natural log e equal to 1, and as a result, we have only our power. So as a result, what do we have right here? We have I times pi plus 2 pi times m, for example, and plus natural log 3. Really great. And right now, the final step, we can easily factor pi from here, and as a result, we have that our natural log minus 3 equal to 2m plus 1 times I times pi and plus natural log 3. As I told before, this is like a complex value. We have real number part, natural log 3, but generally this is a complex number because we have real part and imaginary part, but basically we have a complex value. This is a complex root. Right now, let's plug in this expression into this spot instead of this natural log minus 3. But before this, m is z, okay, from the set of integers, so this is very important. So then we will add the thing right here because we know that k is not equal to 0, k is z, and of course m is also the. So let's plug in this natural log minus 3, let's plug in this expression into this spot. What do we have as a result? Let's split it part because there's like a final part to this question. So x equal to, what do we have right here? We have, let's rewrite it. So we have minus I times natural log minus 3, and all over we have 2k pi. Right now, let's plug in this expression into this spot. What do we have as a result? We will have minus I, we have minus I, times, instead of this natural log 3, we're going to plug in this expression. So 2m plus 1 times I times pi, and plus natural log 3. Really great, and we divide all of the thing by 2k pi. So 2k pi. And we know all of the thing that k is not equal to 0, k is the, and m is also the. Right now, let's simplify this a little bit because I can be multiplied by both of these values, and then we will cancel this I because I square equal to minus 1. Yeah. So right now, let's multiply this I by these parentheses. Let's do this right now. So we have right here minus, and inside parentheses we have I square times pi times 2m plus 1, and plus I natural log 3. And we divide all of the thing by 2k pi. 2k pi. Really great. I square equal to minus 1. So as a result, what do we have? We have minus. We have right here minus. Minus pi times 2m plus 1. And plus I natural log 3. And all over 2k pi. All over 2k pi. Really great. And right now the final step, let's open this parenthesis with the minus before. We have minus. So as a result, what do we have right here? 2m plus 1. So we have right here that our x equal to 2m plus 1 times pi minus I natural log 3, and divide all of the thing by 2k pi. 2k pi. And this looks like our answer, but let's write our final answer with all the thing with when k is integer and m is integer. So let's write our final answer. So let's do this. So let's split this part and let's write our final answer to this challenge. So answer x equal to this expression. So we have 2m plus 1 times pi minus I natural log 3, and we divide all of the thing by 2k pi. But we need to know that k is not equal to 0. So k is not equal to 0. And k is integer, so k is z. K, for example, we can also write it at 1, 2, 3, and m is also the. This is our answer to a question 1 to the x equal to minus 3. We had in the beginning this question, and this is our answer. And this is a very tricky question. For example, if you plug in this question in math library, for example, the most popular math library, for example, if you plug in, you will have like the answer that this statement is false. You don't have this solution. But in terms of math, I think that's really interesting to find your own solution, to work a little bit about Euler's identity. And of course, this is not like a general solution because we don't know what will happen when k is, for example, 1/2. We don't know about it because we know that k is integer, m is integer. We know what happens in this point. We know already, we have answer. But this is not like a full solution. This is not like a general solution. We don't know what will happen, for example, when m is not integer, when m is, for example, 1/2, 1/3, when k is 1/3. This is not a correct solution when k is real numbers, like non-integer number, But when k is integer number, this is a great solution. Yeah, we proved it before that Euler's identity works perfectly right here, because Euler's identity gives us 1 on the right side, and as a result, when we plug in it, this is absolutely correct thing. We don't make a mistake right here when we write this k is not equal to 0, k is integer, is integer. This is absolutely correct answer. Okay, but when k is not integer, k is, for example, real numbers, like rational numbers right here as a fraction. Yeah, we don't know what will happen there. We don't know what about it. But when k is integer, m is integer, this is our answer. When k is not integer, we don't know what will happen there. So this is my thought about this challenge. I hope you understand it. I hope you learned something new. This is like a very tricky, complex question with a complex number, you know. And this is not like a school question, to be honest, because, for example, as I wrote it before, when 1 to the x equal to -3, you're going to plug in natural log on both sides. On the left, on the right side, yeah, you plug in this, and you will have that in the numerator, you have 0. Yeah, you will have, as a result, you will have something like that x equal to natural log -3. You will have something like that. And all over we have natural log 1 in the beginning. Yeah, natural log 1 equal to 0, and we don't know what will happen there because we can't divide by 0 in terms of school. So this is like your final answer on your exam. But maybe my channel watch a lot of teachers, so I hope you enjoy it. I hope you see my approach, and of course you can write your approach into the comment section. It will be really interesting to read about it. It's really like great to see your response into the comment section, because this is like very, very tricky challenge, and there are a lot of approaches how can I do that in terms of complex numbers, and I hope you understand this explanation. I hope you learned something new. So definitely don't feel bad if you got this wrong. I hope you enjoyed this video. I hope you learned something new. See you in the next videos, and have a great day.